So variational auto-encoders, that's what we're going to be doing today. So the first thing I want to talk about is latent variables. So the idea is that we have some data that we can observe, like children are exposed to speech, sounds, but they're not born with a knowledge of the phonemes of their language. So the idea is we want to model something like speech sounds using variables, using interpretations of those speech sounds that we don't have access to. We don't have any training data on it, right? So we're going to learn latent structure that we will then infer from whatever the signal is. So just examples of this. If we're exposed to a bunch of sentences of English, that's another thing people presumably learn. They're exposed to English, they learn the grammar. So the parse tree of a sentence is not given. It's something that people learn from other data, from the raw data of the sentences. We might want to be able to segment an image or construct a depth map or produce a class label. But in all these cases, we might want to be able to do it completely latent, just exposed to the images or just exposed to the word strings. So we want this reconstruction of this interpretation to emerge from observations where it's not present. And we often think, so especially in the Bayesian formulation of VAEs, they think of this latent structure as sort of the causal source of the observation. So we think of the word string as the causal source of the sound, which it sort of is, right? I think something I want to say, and then I speak. So formally, mathematically, what we're trying to do is model a probability distribution over something that I'm calling y. That would be like the sound wave. And we want to model it in terms of latent information, which in this model we're going to think of as sort of the causal source of the thing we observe. So we're going to model the probability of y as a sum over the possible z's of the probability of, where z is the latent information, of the probability of that latent information and the probability that given that latent information, we observe y. Which can also be written as the expectation over, or average over drawing the latent information, like the actual phonemes or sentence, and then generating the expectation over that of generating the sound given the sentence I'm trying to generate. Good. It's moved. It's going to be next time. I was just explaining, I completely reorganized this section of the class this morning. So it should be. I'm working from the website. Okay, good. Okay, so typically we call this, in this language is a little bit arbitrary. We call the prior on Z, we call the distribution on Z the prior, and we call the conditional distribution on Z, given what we observe, the posterior. And we think of Y as evidence about what the Z is. So you can think of the sound wave as evidence about what the sentence is. And that language is part of the language of variational autoencoders. So we're going to make some assumptions. We're going to assume that these two distributions, these are both model distributions that we're going to learn. We're going to learn a prior over Z, and we're going to learn a conditional model of Y given Z. And I'm going to assume that they're both sampleable and computable. These are model distributions. This is not the actual population, right? We're going to learn these models. And I can sort of, since I'm learning the model, I can choose the structure of the model, and I can make the model such that I can sample from it and I can compute its value on a given input. Now, that's not always true. Like for a graphical model, we can't compute the partition function. So it's typically not possible to exactly sample or exactly compute distributions. An autoregressive model, like a language model, you can sample from and you can compute the probability of a distribution. Okay, so we would like to use cross entropy loss. So we have our observations, right, the things we can see. And the fundamental objective is still going to be the same objective. We're still going to talk about trying to train the model to give us the most likely probability of what we see, and as measured by the cross entropy loss. But we've got this form of this probability in that it's an expectation over something we can't see of the probability of the observation given what we can't see. Now, the problem here is that even though we've made these strong assumptions about the prior, that it's sampleable and computable, and about the conditional, that it's sampleable and computable, we don't typically have any way of computing P of Y because it involves this big sum over the hidden information. We also can't compute, although we have a model of Y given Z, we can't compute Z given Y. So that presents a problem for this objective function. How do we train this model with this objective function? And that's what variational autoencoders are all about. So we have this intractability problem for computing P of Y. And what we're going to do is we're going to construct another piece of our model. So there's going to be a third piece of the model that's that's trying to approximate the probability of Z given Y, which is something we can't really, the model itself doesn't let us compute that. So you can think about this as, with the way the Bayesian would think of it is I've got a model. The model consists of a prior over something like sentences and a conditional distribution over sound waves given sentences. And I hear a sound wave and I want to know what's the sentence. And that can be in general. So that's saying, given the evidence, what's the conditional probability of the underlying model given the evidence? And that's the thing that's hard to compute. And that's the thing that Bayesians are really interested in. Given some evidence about something, what's the posterior on the underlying information? And so this whole methodology comes out of something called variational Bayes, where they have a variational approach for estimating this conditional probability of the true underlying posterior. So what we do is we just assume a third piece of the model to model that direction, the inference of the hidden information from the observable information. So we're just going to build a model that does that inference. There's no guarantee that it's correct, right? We're just going to be part of our model and we're going to optimize with respect to it. And so here's the theorem. So this is called the evidence lower bound, or ELBO. I saw a recent paper that abbreviated this to just ELB, but everybody calls it the ELBO. It's called variational because it's a bound. Whenever you try to optimize something and you bound it by some upper or lower bound, and then you optimize the bound, that's called a variational technique. So this is the thing we care about, right? It's the log of the probability of Y. And this first step is just, it's hard to see how you make this first step in the derivation, but it's clear that it's true. This first step in the derivation, I'm going to rewrite this as an expectation over my inferred Z. This is my model of how to get Z from Y, right? So I draw Z from my model of how to get Z from Y. May not be true. And then I ignore it. And instead I write the log of the probability of Y and Z given Y divided by the probability of Z given Y. And this is analytically just the probability of Y. And I've ignored this expectation, so that makes this equation true. This is I don't know, it would be hard when you're doing this to take this first step. Are we okay? So we're drawing from our model. Maybe I'll do one more step and then, or do the whole thing, and then we'll come back and see why I did this. you take this expression, which is analytically just the probability of y, right? I'm multiplying and dividing by the same thing. This is analytically the probability of y. And I take this thing that I divided by, and I substitute the model for it. But when I substitute the model for it, I'm really just multiplying and dividing by that model probability, right? So this sum of logs is the log of the product, right? So this cancels, right? If I take that sum of logs and make it the log of the product of the two terms, that I just multiplied and divided by that. But in some ways, I substituted this real probability with the fake one, and what's left is a KL divergence, right? And a KL divergence is always positive. To mute. Where is it? Oh, okay. Okay, so I multiply and divide by this. It breaks this thing up into two terms, one of which is a KL divergence. The KL divergence is always positive. So if I ignore it, I must get something that's less, that's smaller. If I drop the KL divergence, which is positive, what's left is smaller, right? So then I get this expression and I get an inequality. And now this sampling matters because it appears over here. And that's called the elbow. I said this is the evidence lower bound. So it's a lower bound on the probability of the evidence. We're viewing Y as evidence about Z. Is this making sense? Okay, so this is the elbow. And now what we can write the elbow here, I had written this as the probability of Y times the probability of Z given Y. I can rewrite that as probability of Z and Y, which I can rewrite as the probability of Z times the probability of Y given Z. So this now, all of these terms are now model expressions that I can evaluate and sample from. I'm going to assume I can also evaluate and sample from this model. And you can rewrite that. This is a log of 3 terms. And way back in the beginning of the class, I said, whenever you have a log of a bunch of terms, you can break those terms up because the log of a product is the sum of logs. You can break those terms up in various ways. So this is a standard way to break this up. This part of it is a KL divergence. What I've done is I've kept the 2 Z terms and pulled the Y term out. And this is, so I get a KL divergence here. And I flipped the sign of this and I flipped the sign of this and flipped the sign of this so that we're looking at the cross entropy loss now. So this is the thing I'm going to try to minimize. There's a problem. I'm tempted to ask if anybody can see a problem, but there's a problem here that's a little subtle. We want to optimize this with respect to the model parameters. And some of the model parameters appear in the distribution we're sampling from. Now that wouldn't happen in a normal cross entropy objective function. Because normally you're sampling either from a training data or the population. So you've got a well-defined sampling distribution. Here, we're sampling from the model. So how do we do backpropagation into this position, right? That's where we're getting our sample. We can backpropagate into these values that are computed from the parameters and update so to reduce this. But there's no easy way, or it's not immediately obvious how to backpropagate into the use of the parameters right there. So there's something called the reparameterization trick. And I'm going to just do this once and then we'll sort of ignore it. So the problem is doing gradient descent into these parameters when we're sampling from that model. So instead of sampling from that model, what we're going to do is sample from fixed noise. So typically you sample, for example, and often you sample from a Gaussian, just a simple isotropic Gaussian identity covariance matrix. So you sample some noise, and then you sort of define the probability of Z given Y and the noise. And because it's looking at noise, the variation over that noise, the different possible values of the noise define different possible values of Z. So instead of sampling from Z given Y, I sample the noise and then compute Z from the noise. But it's still a non-deterministic computation with respect to Y. No, that has to do with discreteness and discrete latent variables. So I'm not yet talking about that problem. We're going to get to that problem. Yeah, if Z is discrete, these have problems. I want to postpone that issue of whether, so if, no, it's fine. I love questions. If Z is discrete, then we've got an issue, because a discrete choice for Z is not going to have a continuous, it's not going to have a derivative with respect to the parameters. But I'm ignoring that today's lecture, right? So we'll think of Z being continuous today. This is a, so if you've taken a course on a question, good. Because if this expectation down here is over noise, and that noise has a fixed distribution that's independent of the model parameters, then there's no, I don't have to worry about back propagating into the distribution. The distribution that I'm drawing from is now fixed. Y is drawn from the population, and the noise is drawn from a fixed noise distribution. So the only, and so I just have to calculate, but drawing from this fixed noise effectively draws Z, right? Because then you can compute a probability distribution over Z given Y and the noise. Okay, if you've taken a course in machine learning and you happen to have seen EM, there's a very close relationship between EM and variational autoencoders. So EM is just alternates maximization of two models, or optimization, I should say. So this is the VAE. This is what we just looked at. This is one way of writing it. In EM, you've got this, you also have this joint distribution. EM is also about latent variables. And in EM, you alternate two steps, an inference step and an update step. And you can think of the inference step as optimizing your generation model, right? So you set your generation model to be equal to the probability of Z given Y. You assume that everything, in EM, it's typically the case that everything's very tractable. And so you can actually calculate the true conditional probability of Z given Y. Like in Gaussian mixture models, you actually calculate the true probability that each point is in each class. Or in grammars, you can calculate the true probability of a given parse of the given sentence. And if you can calculate that, then I can think of that calculation, the inference step, as optimizing the model of Z given Y. Then what you do in EM is you hold that model fixed, right? You hold the model that's generating the data fixed, and you update the model of your model of Z and Y. And that's the M step, the maximization step. So if you've seen this before, I just want to point out, and just let me say it at a high level, EM is alternating optimization of the two pieces of the model for a VAE. And in the case where those two optimizations are tractable, you get this exact but alternating optimization. Good. It's much better if I get questions. Psi, we're optimizing psi there. So this is setting psi to be the optimum given phi. And when you set psi to be the optimum given phi, you're setting it to phi. So since the inference step is done first, we're setting, we're computing this probability distribution. Instead of using some made up model, in EM, you can actually compute the true with respect to the true phi, conditional of z given y. So that the optimum here is going to be the conditional distribution defined by this model. So if you look at this update equation, this is the EM update equation. EM update equation iteratively updates your model parameters. And in EM, your model parameters are the probability of z and the probability of y given z. It's just phi. So EM just updates phi. It says the next phi is the minimum of this expression, where you hold the data generation fixed at the previous phi. But then you optimize the model to best fit the z as generated from the true distribution of the previous model. If you haven't seen EM, EM is one of the most complicated, subtle things that is taught in an introductory machine learning class. In my experience, people who take machine learning always struggle, especially when you do it in general. You'll understand Gaussian mixture models, sort of. But then you write down the general equation. It's tough. This is the general equation, right? This EM, this is a general equation. And so what you do, what I'm saying is that this general equation can be broken down into an inference step and an update step, and the inference step involves calculating this distribution. And calculating this distribution is optimizing this model to be phi's model. So you can think of that as a question. I'm sorry, say that again. Well, EM is typically used in a setting where there's a closed form solution that takes you all the way to the optimum on psi. So EM is doesn't typically involve any kind of gradient descent or optimization. But mathematically, it's equivalent to, it's just the case where a closed form optimization of psi is available. That answer your question? Another thing that happens in EM is you think of Z, in EM, you do a whole pass over your data when you do an update. Whereas I've written this just in terms of ZY pairs, but you can think of Y as all of your observations and Z is the latent variable for all of your observations. And then in that view, this is, you get this update equation. So in practice, I think you just do it until it quits changing. I'm sorry, which step you want to talk about, the inference step or the update? Yeah, so VAE is just going to be taking gradient. It's just going to be doing SGD in general on this objective function. All I'm doing here is sort of, if one is familiar with EM, I'm pointing out that EM can be viewed as this alternating optimization of the elbow of a VAE. And that, since I've, another thing to note that I should have pointed out is that the optimum for this is when this KL is 0. If this KL is 0, then you get equality, right? And the KL is 0 when this is exactly the true distribution. So the optimum for the, if I'm just optimizing my model of Z given Y, the optimum of that derivation is the true conditional probability. And that comes up here. If I optimize this, the true optimum is the true conditional probability. The elbow, what we want to do is minimize the cross entropy loss to the distribution that we observe. We sample from the population, we get a probability of the thing we sample. We want to maximize the cross entropy loss. The elbow gives us an upper bound on that cross entropy loss. And if in that upper bound, if our model it's generating Z from Y, if our inference model that's generating the latent data is correct, then that upper bound is actually, you get equality, not an upper bound. If your inference is correct, it becomes equal. So the idea is that we now use SGD to minimize that upper bound. And it has, if you assume universality, the minimization of that upper bound will converge to the actual cross entropy. If you assume that anything, that it's universally expressive and that SGD solves it exactly, it will still converge to the true cross entropy. Okay, now we're going to start talking about other problems. So there's another problem. So I should mention 3 problems. One is if you're sampling from a model, you have to figure out how to solve that problem, how to do gradient descent into the model. The other problem is that we often are dealing with discrete latent variables, and that inference process is not differentiable. There's a third problem. And the third problem is called posterior collapse. So, and this is a real problem in practice. So suppose you're doing SGD and you converge on a model that deterministically determines Z from Y, right? So, and not just deterministically, it always picks the same Z. Like, it always picks, there's some fixed Z that it's always picking, like an empty phoneme sequence or something. Well, it also, so in that case, if it's always picking the same Z, then this probability is 1, because it's always picking the same Z. And this probability is 1, so this term is 0. Right, so if it always picks the same Z, this term disappears. And if it's always picking the same Z, then the probability of Y given Z is the same as the probability of Y. Right? Z doesn't tell you anything. So now it's up to the model to compute the probability of y. But the model, if you assume universal expressiveness, the model can do that. It doesn't need z. Am I making sense? Under universal expressiveness, there's no need for z. So, and so this actually happens in practice. The model, you get a model that, especially this would happen, for example, if you're trying to learn parse trees this way. Some language model is going to be able to model the probability of the sentence pretty well. And it's going to be very hard to get that model to improve its probability of the sentence in terms of a latent parse tree. So what happens is the inference of the parse tree collapses and the model just predicts the string. Okay, for various reasons, one of which is posterior collapse, people have tried to play with VAEs a little bit. So there's something called the beta VAE. So the beta VAE is just the VAE with this additional hyperparameter, beta, which allows these two terms to be weighted differently. And if you set beta less than 1, right, so you put less weight on this cross entropy term, it might help the posterior collapse problem. The original paper on the beta VAE wanted beta greater than 1 that may improve interpretability. And exactly, and a lot of people, this is very common now. You get this extra hyperparameter and you can play with it and get your model to do more interesting things. For a long time, I was kind of confused about exactly how to think about this hyperparameter, but the right thing and the real reason these slides needed to be rewritten, I think, is because of this phenomenon. I'm calling this an autonomous encoder VAE. So the idea here is, what I'm going to show is that if you fix your encoder, okay, so why is this, I don't think I ever said why this is called an autoencoder. This model that's generating your model of inference, right, from your evidence Y to your latent structure Z can be thought of as an encoder. And then the probability of your observation given Z is a decoder. And both of those occur in your model, right? If we go back to the, what a VAE is, this is your encoder, right? Your encoder here is encoding Z. This is your decoder, and there's this other piece of the model, which is the prior on Z. So this is called encoder autonomy. So the idea here is you take an arbitrary but fixed encoder, right? Fix the encoder. It doesn't have to be degenerate. It can be very meaningful. And consider optimizing the other parts of the model. And the claim is that for any fixed encoder, if you assume universality of the model will still converge to the actual population distribution. The encoder can be anything, and if the model the rest of the model, if this phi is universal, it can do the right thing for that encoder. So basically you can show that if I'm holding this fixed and I'm considering the probability distribution defined by the population on Y and the encoder on Z, right? So I'm defining the distribution I want to model differently, right? I'm not saying it's the prior on Z times the probability of Y given Z. I'm saying, no, it's the population on Y and the generated distribution on Z. So that gives me a YZ distribution. And if I optimize this piece of the model, it can be shown that the optimum here is the marginal on Z defined by this distribution. And in that, and also the optimum here is going to be the probability of y given z. And those two things together imply that if I take this prior times this conditional, I'm getting the true distribution on y. That this is the prior and this is a conditional under the same distribution on z. I was felt this happened like 2 years ago. I haven't seen this in the I have not seen this in the literature. 2 years ago, I realized this was true, that this would model y, in principle, would model y well, independent of the encoder. And it was, I don't know, felt like a big revelation to me. So what I can do, if that's true, if no matter what the encoder is, this can model y well, then I can add whatever loss function I want on the encoder. And in principle, I'm still getting a good model. Okay, when VAEs were introduced, and I said today I'm thinking about everything being continuous, they were introduced with Gaussian densities. So here's the VAE. It's got this KL divergence in it. And you make all of these Gaussian densities. Okay, so I'm just written down what it means to be a Gaussian density. We're going to have diagonal covariance matrices to make life simple. And so let's think about how this works. The probability over z is just going to, the prior on z is just going to be a Gaussian. Its ith component is just a one-dimensional Gaussian with a variance that depends on the ith component. The model's allowed to pick that variance. The probability of z given y is done in a funky way. We compute some estimate of z. The model computes some estimate of z, which I'm calling z hat. So this is the inference step. I'm computing z from y. It computes a z hat, and then it, well, that's just a point, but I need a probability density. So I take that point and I add Gaussian noise. So the probability is proportional to the amount, the probability on z is proportional to the amount that z deviates from the predicted z. Take that squared divided by 2 sigma squared for that component. And that's how we get a Gaussian. We get a Gaussian centered at this z hat. And we do the same thing for y. To predict, that should be a phi. To predict y from z, we predict a y and then take Gaussian noise and then take a Gaussian distribution around our predicted y in each parameter. Is trivial? No questions? What do you want? The last line? Yeah, so this should be phi, but I'm modeling the probability of y given z. So the question is, how do I do that? I take my z and I pump it through a deep network. It produces an estimate of y, right? That's what we've been talking about before. But I don't want a point, I don't want all my probability mass to be on that point, because that's just some real vector, say. I want a nice smooth probability density. So I take that point and I say the probability of the true y given z is going to be a Gaussian distribution centered at that point. And so that's how I'm computing. So both the probability of z given y and the probability of y given z are a network computes a prediction, and then you put a Gaussian distribution centered at that prediction to get a Gaussian density for the conditional. Oh, and here's a weird fact about this model. So now we're talking about Gaussian models, right? So all these probabilities are Gaussian. Now everything's differentiable. So we don't have any problem with non-differentiable discrete latent variables. You take that model that I just defined, this model in the prior allows an arbitrary mean and variance for each component of Z, right? So the prior is also some point in Z space and some big Gaussian around it. Without loss of generality, I can take the prior to be just normal 0I, right? So a weird fact, without loss of generality, the Z can be, the prior on Z can be just normal isotropic. And you can show that by analytically solving these KL divergences, this is the only place where the prior appears, is in this KL divergence. So you can, by computing these KL divergences, you can reparameterize the generation of Z given Y such that its marginal is such that the prior becomes just this Gaussian at 0 with an identity covariance matrix. So when you read papers, they'll always take the prior on Z to be a Gaussian with an isotropic, with an identity covariance matrix, but there's no loss of generality there. Okay, this is when VAEs were first introduced. A nice thing about a VAE is we've assumed all our models are sampleable, so we can sample from the prior on Z. So in this paper, the prior on Z was just an isotropic Gaussian centered at some face, not centered at a face, centered at some at 0. So we sample from a Gaussian centered at 0, and we compute the probability of the face given, we predict a face from that point, right? There's a model of Y given Z. So that's going to be a deep network. That deep network is going to take this random noise Z and estimate a face, and then we're going to take some Gaussian noise around that face. And I think in these pictures, they're probably not even taking the Gaussian noise around that face. They're just showing you what face is predicted. So 2014. So these Gaussian models for faces had some problems. As you've seen, this is going to get a lot better over time. This is 2014. All right, so this is a bunch of slides I had on differential entropy. So we haven't really talked about this case where you're computing a cross entropy to a density rather than a discrete distribution. And we haven't really talked about differential entropy, and differential cross entropy. So differential entropy is an expectation of a minus log density. But if you think about it, the probability of a point under a density is actually 0. So if the probability of a point is actually 0, one can argue that this should be infinite. But anyway, this is the definition of differential entropy. And there's a differential cross entropy also. So as an example of this, just to indicate why there might be some pathology, consider a uniform distribution on an interval of width delta. Now the density there is going to be uniform. It's a uniform distribution, it's a uniform density. The density is 1 over delta. So that delta times the density is 1. So if the density is 1 over delta and I apply this definition of entropy, I get the expectation over X of minus log 1 over delta. Now as delta goes to 0, the density goes to infinity. And when the density goes to infinity, once the density is greater than 1, we're getting negative numbers here. So what happens is the differential entropy as delta goes to 0 goes to negative infinity. Differential entropy can be negative. And differential cross entropy can be negative. And the same thing happens with a Gaussian distribution. So this is just saying, what's the entropy of a Gaussian distribution? And I guess I don't want to go through this calculation. You can look at the slide or calculate it yourself, but intuitively, a Gaussian distribution is sort of analogous to a uniform width distribution where the width is roughly the standard deviation of the Gaussian. And that's the answer that comes out, that the entropy of a Gaussian goes as log of the standard deviation of its width. So as its width goes to 0, we have that h goes to infinity. I think there should be a negative sign there. Something went wrong. That happens when I do it this morning. Yes, there should be a negative sign in front of that log. Oh no, sorry, that's right. That's right, sorry. Sensitivity to the choice of units. This is a weird thing, right? You want to define a probability distribution over lengths. And I can measure the lengths in meters or in inches. And if I measure them in meters, the number of lengths per meter is going to be larger than if I measure them in inches. The number of the probability of landing in a certain inch interval is going to be smaller than the probability of landing in a certain meter interval. And so what happens is the entropy as measured with differential entropy is going to be different or sensitive to the choice of unit, which seems strange, right? Units affect the entropy. This is just to point out that overfitting is possible. So if I've got a finite training set and a really expressive model that's producing a continuous density, right? The finite training set is a set of points. And what the model could do if it really wanted to, and this happens in Gaussian mixture models, right? If I have a Gaussian mixture model that one of its mixtures has only one point, then the model can take the variance of that and drive it to 0. Right? It can mean the Gaussian mixture around this one point can have width 0, and the density at that point goes to infinity. In which case, the cross entropy loss that you're optimizing goes to minus infinity. And anytime you've got a bunch of discrete points, if the model can start modeling those points, have a density for each point, it can drive the density for that point to infinity, and the cross entropy can go to negative infinity. So it makes me uncomfortable. There are ways to fix this, but it makes me uncomfortable to be minimizing something that can, in principle, go to negative infinity. And it can, it could happen for some subset of your data, or, and I really do think you want to think of differential entropy as infinite, right? If you think of taking the real line and dividing it into little intervals, then your continuous density is going to give you a discrete density over the intervals, a discrete probability distribution over the intervals. Each interval will have a probability. As the intervals get smaller and smaller, the discrete entropy goes to infinity, right? Because the number of items goes to infinity. So if you consider a uniform distribution, you're going to get a uniform distribution over the little intervals, but the number of elements is going to infinity. So the entropy is, so I think of differential entropy as infinite. Okay, but KL divergence is meaningful. So this is the definition of KL divergence. Now I'm looking at continuous differential KL divergence. So differential KL divergence involves a ratio of probabilities, a ratio of densities in this case. And even for densities, KL divergence is always non-negative. And in particular, KLPP is always equal to 0, independent of the differential entropy of P. Mutual information. Mutual information, when I first encountered it, I kept trying to get my head around it. It's intuitively the amount of information shared between two random variables. What the hell, whatever that means, right? It has this formula that defines it. And it really does, there are all kinds of equations involving mutual information, and it really does help to just think of it as the amount of information that's shared. How much do I learn about one variable when I know the other variable? How many bits of information on average do I gain about X when I look at Y? That's the way you want to think about it. And it can be defined, one way to define it, is as this KL divergence between the joint distribution and the product of the marginal distributions. So mutual information, because it's a KL divergence, is happy to be to work with densities. And we're going to see mutual information is closely related to the Shannon channel capacity theorem back from the 40s, and we're going to talk about that next time. The data processing inequality. So what intuitively for discrete distribution, what the data processing inequality says is if I've got a random variable over discrete values, and I take that random variable and apply a function to it, right? So I get some value of that function. The entropy of the value of the function can only destroy information. Can map two things to the same thing. So it can be forgetful. So the entropy of the value of the function as a random variable, when it's applied to this, gets smaller. Right? The entropy, the data processing inequality says if you apply a function, you can't create new information. The entropy of the distribution cannot go up. For a continuous variable, this is not true. This is perils of differential entropy. If I take a real number and scale it up, it gets wider, right? And its entropy gets smaller. If I scale it down, it gets narrower and the entropy gets, if I get to say that right. If it gets wider, the entropy gets larger. If it gets narrower, the entropy gets smaller. And it can go to negative infinity. So the data processing inequality fails in that form. However, there is a data processing inequality for continuous variables, which is stated in terms of mutual information. It says that if I take a function of a variable, y, and look at the mutual information from y to some other variable, right? So what does y tell me about x? Which in the continuous case is a meaningful thing to say. And I look at what y can tell me about x versus what f of y, z, can tell me about x. Z is always going to tell me something no more than y knew, right? Z can't have any insight into x that y didn't have because z is just computed from y. If I can use that language.